Well, now let's do the talk by Professor Antonio Sergio de Castro from the State University of Ponta Grossa. The talk is entitled Analytically Solvable Time-Independent Hamiltonian with SU2 and SU11 symmetries.
Okay. Okay. Are you listening? Okay. My voice. Okay. First of all, I would like to thank the organizer for the invitation, Alexander Dodov and Professor Dodov. And as Andrei said, I is not honor as obligation, okay, to stay here to present something we believe is be interesting. So this is my laser. Oh, sorry. Okay. Oh my God. Okay. This is my city. Okay, Palermo in Italy and Brasilia. I noted something similar here. Okay, between between Brasilia and Ponta Grossa. Okay, something similar. Okay, okay, let's go. Professor Dodonov recommended me to work at Palermo with Professor Messina. When I stayed there for the first time, Professor Messina asked me for to search something interesting to study. So I got a lot of papers, read many papers, and one of the papers of Professor Messina and Professor Agazato, I find these words, solvable Hamiltonians for quantum two-level systems. So I'm very interested. I was interested in study exactly method to solve the equation, the differential equation. So in this way, this work keep my attention and create a motivation for my research. First, understand the rule of symmetry in quantum mechanics. Identify a class of analytical solvable time-independent Hamiltonian operator, okay, for finite dimensional, infinite dimensional Hilbert space, and also SU symmetry systems, which it will be interesting to find a way to solve exactly this kinds of system. And after about the suggestion, Professor Messina, to apply it to Jaynes-Combs model or any kind of coupled quantum systems. In this presentation, I will show or what we call Messina-Nagasato ansatz. Professor Messina called trick, but the trick is for magician. Okay, ansatz it's more convenient for research. And the parameterization of the solution obtained by the Messina-Nagasato ansatz. And after this, we'll show how the results obtained in this study help us to solve time-dependent Jaynes-Combs model. Of course, we solve the obtained exact evolution operator in the resonance case. And also, I will only point in some papers, some we have published concerning the coupled two-level system and quantum transition. Of course, okay. When we look, I will concentrate only in the SU2, S11 two-level systems, of course. So when we look at the Hamiltonian operator, in this case, we find that the Hamiltonian operator is right in terms of the operators. It belongs to the algebra, okay, concerning to any of these two, SU2 and S11 two-level system. Of course, this is the algebra S plus 1 is concerned related to SU2, minus is related to S1 Okay, there is a similarity between these two models, but physically a great difference. Okay, so when we look, when taking any time-independent Hamiltonian operator with the alpha G arbitrary functions, the normal route is to substitute in this Schrödinger equation for the evolution operator and solve this and obtain the evolution operator. But here we have a problem because this generates a system of differential equations with time-dependent coefficients in general is not easy to solve. Sometimes we can use approximative methods like average methods of Bouguereau. Multiple scales. So it is, I use this in other models. I studied with Professor Rodonov, but sorry, this keep my attention. Is there some way to find, okay, time-independent Hamiltonian operator which can be solved exactly? Then that paper I presented initially, Professor Messina and Nagasato start considering that the Hamiltonian operators is writing as in these forms involving here the evolution operator, which implies in the systems of equations. Okay, here we present, okay, I will do this only for SU2 symmetry. Okay, now the Hamiltonian operator is written in these forms with the longitudinal field, a transversal field. For this, the Hamiltonian operator have the evolution operator right in this form. Due to SU2 symmetry, we have the A modulo A square plus modulus B square equal 1. This condition is fundamental for the SU2, whereas for the SU11 we have minus here, okay? So the idea behind the methods of Messina Nagasato ansatz is that we have the longitudinal field and transversal field related to A and B in this way. So we take this equation and note that a transversal field over A square can be written in this form, so time derivative of the ratio B over A. This implies that we can write, okay, B can be written as a minus I times A times X. And X is defined in this way, involve the transverse field and the coefficient A. These conditions imply that this must be satisfied. So not here, this condition involves only A and X. But the question is, what is the advantage of the X on this approach? So, field and make choice about the form of X and put here, solve time a solution of A which depends of X and the longitudinal field. I will speak more slow. Okay, so in this way, for a given X and omega, we find B because we solved this equation, and this also fixes the omega, the transverse field. So the idea, introducing the function X, is the ansatz originating some time-independent Hamiltonian models for which simultaneous explicit calculation of the evolution operating start forward. Okay, in this way, by these methods, we make appropriate choice of X for capital omega fixed, and we find the solution. The question is, okay. Sorry, in the integral. Imaginary part here. No. T times. Sorry. Yes, because I apologize. My computer is configured, so some problems will appear here. Okay. Then, in the Messina Nagasato ansatz, we have to analyze the kinds of functions, possible functions. The first one is a real function. The real functions implies we assume the X is a real. We substitute in the equations. We find that X must be this form. Of course, we restrict the condition that this is blue terms must be real to be solved. Okay, there is okay. there is a lot of consistency condition which must be obeyed in order to this work better. So for the real functions, we have the form. So they have the solution. Okay, we can now put some transverse field here, longitudinal field here, and the solution is easily constructed. We solve exactly. And at the same time, we define the transverse field for which this is, how to say, for which the Hamiltonian operator is exactly solvable. Another possibility, considering in the method, is the function with this form. So, okay, we have the mu parameter here, a phase real function phi here, and appearing here in this exponential. So, for complex function in this form, also it's possible to find the solution parameterized in the form a equal this is expression here involving the cosine of this phi function. The phase well defined also. B appears in this way with the phase determined in terms of longitudinal field and transversal field. Now, the phi is defined in this way. Of course, here the integral of time, okay? Integration of time. But these solutions works only if this condition is satisfied. Okay, the modulus of the transverse field must be equal to the longitudinal field plus time derivative of the coping phase. This must be satisfied. If you put longitudinal field and transversal field did satisfy this condition, the solution is ready to be used. Okay? Now, okay, but we can consider also the complex general function. We call the parameterization of second type. This is more difficult because for general functions, this second parameterization implies that the A is given in a complicated form, and B also is obtained in this way. Depends of A, the form of this A is defined. Capital A is defined this manner, okay, involving the theta function. Theta functions appear here. So these theta functions is difficult to be obtained because theta must satisfy this integral differential equation. Here it's a complicated problem because if you, for example, fixed some omega, and also assume some transverse field, we must solve this equation in order to obtain the A and B. In the sense, this is the Messina-Nakasato ansatz. Okay, what's the message? We have obtained the solution, okay, the solutions of the evolution operator for a SU2 Hamiltonian operator, but in two important cases, the parameterization of first type, okay, but where this condition must be satisfied. Another solution, the parameterization of second type, the A and B, the elements of the evolution operator are well defined, but theta must satisfy this integral differential equation. We're working around 6 months trying to solve this equation. It's not easy. Recently, I try again, and perhaps, I'm not sure, I find some special case involve the Hoyne functions. It's not a trivial problem, okay? But what is important here? We have not the solution, but we have the possible longitudinal and transversal field where the Hamiltonian operator is exactly solved. Okay. Now, since we have a Hamiltonian operator, a method to find the Hamiltonian operator, the question is, where can we apply it? What is the reason for this? So, and then we look at the Janus time-independent coupling. So, again, we look at the algebra of the system, and we find that for the systems, we have this operator number. Sorry, this operator number here, right in terms of the bosonic variables, and here the operator JZ and the identity. On the J here is a number. We all noted that for this Hamiltonian operator, this number operator commutes with the Hamiltonian operator. This implies that the n, sorry, it's complicated. N is conservative quantity in the model, so that like when we solve it, try to explain. When we solve the hydrogen atoms, we look at the angular moment and the z component of the angular moment. What happens? We find the invariant subspaces for L equals 0, for L equals 1, and so on. So the same happens here. This operator N defines a set of invariant subspace, okay, the spectral citation number, where we can write this is eigenvalue with the Fock state number, and this is parameter R. R varies from 0 to 2j. Of course, when j is 1/2, we have R varying, assuming the value 0 and 1. And this implies that all invariant subspaces determined by the excitation number operator are two-dimensional. What is our conclusion? We have a two-level system. For each value possible for n, okay, we have a two-level system with SU2 symmetry. So, in principle, okay, but now, well, how can we construct the solution? Using the projectile operator associated to each invariant subspace, we can see, it is a simple quantum mechanics exercise. We can see that the Hamiltonian operator is was a combination of the operator defined for each invariant subspace. Okay? Now, the total evolution operator of the system, it is also right as a complex direct sum of the evolution operator associated to each invariant subspace. So there is a relation. But okay, for each invariant subspace, we have the Hamiltonian operator and the corresponding evolution operator. So in the two-level atoms in quantum mechanics, this is James Campbell's model. We have here, okay, the basis for each invariant subspace. And what is interesting, the Hamiltonian operator in each invariant subspace can be written in the form. Okay. This is only a global responsible for a global phases, and here we find the two-level systems. Okay, with SU2 symmetry in the solutions. We know the solutions. We have to find the solutions. Okay. What's this mean? For each invariant subspace, we apply the Messina-Nagasato ansatz. Okay. Only with this detail here. The transversal field depends on the L, okay? L here, and this is exponential of the phase phi corresponding to L. Only, and here we have a scale factor, okay? The capital omega depends on the cavity field and atom field. But now, what we have? We have the parameterization of two types. The first one is very simple. This one. Okay, this condition must be satisfied. And the second type, parameterization of second type, but we have solved the integral differential equation, which is not easy. Okay, we fix our tension in this case here. But in principle, there is a problem here, because we have an infinite number of invariant subspaces. In principle, you have an infinite number of parameters, n. But now, we look the right-hand side, in which invariant subspace we have the capital omega and the phase of the coupling. This is the same for all invariant subspace. This is help us to see that each of the parameter n depends only of zero. So we have the infinite numbers of invariant subspaces. We have the infinite number of SU2 system, but only one parameter, zero. This is important because if you had infinite number of n, it is also almost impossible to solve exactly. Okay. Now, but for the parameterization of first type, we have the solution. Okay. For each invariant subspace, we find the exact solution for A, modulus AN, modulus BN, and the corresponding phase phi AN, phi BN. Okay? With this in hand, it's easy to solve. Only we define here the kappa is a dynamical time scale. Okay? This is sometimes convenient. Not that the integral involved here depends of the coupling, okay? Time-dependent coupling. Now, okay, we analyze for this system the atomic population inversion under resonance, okay? Because resonance it's important because it's more easy to solve, okay? We also solve it for the case of resonance, but the problem is that for the resonance case, we can write the dynamic in terms of this dynamical time scale. Okay, it's more easy to present to see the consequence of the solution. So we write the exact form of for atomic population inversion for the atoms in ground state, also in the atom in excited state, and okay, we plot. Now we consider the atom initially in the coherent state, the photon number equal 10, and we observe that the red line is equivalent when the mu 0 is equal 0. This is the usual case of Jennings-Cummings model, the solution for time independent model. Okay, we obtain this one here. But now, when the mu 0 is different from 0, for example, we have mu 0 for 4, we noted that the revivals, okay, the atomic population goes to the non-zero values here. We have the revivals of collapse and revivals. So this is the numbers of collapse and revivals increase here. And of course here for the ground, for the atom in the ground states. And now we have here increasing more the value of mu 0, okay? Not that increasing the value of mu 0, the atom is protected for the influence of the field, okay? We take a value mu 0 equal 10, but we plot, no, it's not plotted here, but I calculate with mu 0 equal to 15, okay? Then some way we interpret this parameter me here as such that increasing the value of me, we protected the atom of the influence of the field. Okay, this is for the first consequence we obtained solving these problems with Messina Nakasato ansatz. It's interesting in this model the second solution here. Okay, we are investigating also this equation. It's not easy to find to determine the solutions for theta, but we solve it numerically. Okay, and it is very interesting. Of course, we are not sure about the solution we have obtained because we have to check the program we are using for generating the numerical solution. This is my weak point. Okay, I'm learning with the Professor Celso some new methods. Okay, Celso. Perhaps in future I'll be more able for this. Not. Okay, then this is the first model we solve exactly. Okay, time. Other problems the Messina-Nakazato helping us to solve it is we find the class of exactly solvable generalized semi-classical Hamiltonian systems. We associate the longitudinal field with the component Z of the angular moment and the magnetic field. This is transverse part of the field, relate the component X and Y. So it is also possible to describe precisely the dynamic for some configuration of magnetic field. We have the behavior of the magnetic field in this figure, and define the probability transition for from plus to minus. Okay, so this is behavior. Remember the Landau-Zerner-like transition. Of course, we have another. So we consider this is behavior of the magnetic field, and obtaining the time behavior of the probability transition. And also we have this configuration. Okay, we have constructed and obtaining exactly the probability transition. So what is important here? By means of the Messina-Nakazato ansatz, it was possible to solve exactly and describe exactly the behavior for probability transition for different configurations of magnetic fields. This is very motivated results. So we, of course, this is not important now. So we question about the S11. It's possible to give some description of the S11. Okay, we consider the S11, but now what difficult, some questions appears here due to the fact that these Hamiltonians are sometimes describe an emission PT symmetric Hamiltonian. In some way, by means of Messina-Nakazato ansatz, we consider the Hamiltonian operator. We find the evolution operator. Okay, we find the A and B. Okay, but now what is interesting is that in this parameterization we write in different way. Okay, here. The evolution operator, we find that this evolution, the solutions that appear here define the coefficients of the evolution operator, satisfy the Riccati equation. Okay, and this Riccati equation is integrable if this condition is satisfied. Okay, not different from mu vary from 0 to infinity, but now ni varies from 0 to 1. We have the trigonometric regime. And ni varying from 1 to infinity, we have trigonometric regime. Okay, this is the different regime we find in the solution. Okay, this is a particular case, and of course we try to give some interpretation for the transition probability, but now due to the fact that this Hamiltonian operator be S11 symmetric, we have to note that this corresponds to a complex transverse field, and for this complex transverse field, we find, okay, for different regime, nu equals from 0 to 1, we have hyperbolic regime here, and here we have trigonometric regime. Of course, we extend our results here in these papers. It's a direct application. We solve the Messina-Nakazato ansatz for S11. Of course, note that the A and B, the coefficients of the evolution operator now, is also determined. We find first the parameterization of the second type. Not that here we have the hyperbolic cosine and the hyperbolic sin. But like in the S1 2, we have this integral differential equation which must be solved. In general, this is not easy to be determined. So this is, we don't work in these cases, okay? Only the S1, 2. But okay, analyze some concrete examples for determining A and B noted here. Since it's not possible to solve the integral differential equation for determining the theta function, we impose some behavior for this integral, okay? Arc ascending hyperbolic of Q. Is defined in this way, the dynamic time scale. And we find that A and B is right in this form. Not that theta is not defined, but if you use only modular square of A and B, means that this is not relevant for our purpose, okay? With this, another concrete example, we find you impose this for theta function. This integral is arc sine hyperbolic sine of the Q over 2. Again, we find the A and B, but now these solutions is interesting because this is valid only if the capital omega is O modulus omega. So this is no more this a condition, okay? Because the time derivative of phi here is 0, and this is a particular case of the parameterization of the first type. So the parameterization of first types is a solution inside the parameterization of second type is more general. But so what's the message here? We can exactly solve the S11. And of course, we have the behavior. Of course, we have to consider normalize the density operator here, because of course we are considering the case of a no-emission Hamiltonian operator. And again, we have the behavior of transition probability, okay, for the first example here, okay, and the probability transition, of course, here, and the second example. In summarizing, we find exact solution for SU2, S11. SU2 help us to solve the time-independent James-Common model. For any time behavior, it's possible to construct the solution. Numerically, it is not difficult, it's easy, but we are interested in find analytical solution, analytical description of the solution. And the last paper, I only indicated here. This was very interesting work. We use the Messina-Nagasato ansatz to observe the quantum phase transition for integrable quantum hub-like models with two interacting qubits. This is very interesting because we look for this model, okay? We have two qubits. We have a field. This is coupling occurring here. The coupling occurring here with the mode and the system 1, system 2. We identify the invariant in the model and split this, rewrite the Hamiltonian operator in two independent Hamiltonians in different subspaces which are orthogonal, okay? But what is interesting here is that we apply the Messina-Nagasato to solve it, and of course we described a very interesting result is this quantum phase transition by changing the parameters in the for define the eigenstates. Eigenvalues of the system A and system B, we observe the transition for magnetization equals 0 to magnetization equal -1. Okay, so all this is works I presented now are the examples of problems which were solved by using the idea behind the Messina-Nagasato ansatz. Okay, what is my ambition? Okay, I like to do computations. I like to study this is the representation theory. In now, I'm motivated to extend this result for other symmetries. I'm studying this moment the SL2C, the symmetry SL2C, and SU3. Although Professor Klimov says me this is difficult problem to be solved, but my intention is to find it. Okay, this is the results we have obtained with the Palermo group. So thanks to Professor Donov for everything. It's important. Okay, Professor I know Professor Donov in a dark moment of my life. Professor Solomon knows this history, and Professor Donov was very patient and very professional and a very important person that gave a light for me and conducted me to a better situation. Okay, if I'm here, Professor, this is do you so okay? You changed my life so much. Okay, and okay, train me to work hardly. Okay, in general, my presentation is in English is complicated. I apologize for this. I don't know why. Okay, but I'm a little ashamed, okay? When Portuguese I speak well, but in English is difficult. I don't know. No, I try. I did a lot of courses in English, but I don't know why. Okay, Professor Donov, I consider you a friend, or if you permit, you are like a father for me. Okay, yes, yes. Thanks to Professor Messina. Professor Messina is my uncle. Okay. Okay, Professor Messina is my uncle. And here, sorry, I thank also to Roberto Grimaldo, Professor Agostino Migliori, David Valente, Professor Hiromichi Nagasato, and thanks and for the attention and apologize for my presentation in general. It's complicated for me. Thank you, Professor. One talk moment, Professor. Do you remember 10 years ago I told you you were the sun and I was the asteroid. Yes, I turned around. Yes, you're in the table. I told you. Now I'm happy. My mass is okay increasing. So perhaps now I can be considered a planet. Okay. Thank you very much.